In this module, we are going to go through some of the key enablers for industrial IoT, and the basics of which we have already gone through in the previous lectures, but we need to understand these key enablers in little bit more detail. And so, we will start with the sensing. So, sensing is the, I would say that it is the most important element in industrial IoT, in smart applications and so on. So, we will start with sensing and try to understand how these sensors work and what is the utility of these sensing elements in the overall smart IoT, industrial IoT applications. So, if we take a recap of the IIoT features, we have in IIoT we are talking about large number of industrial machines, connected machines having different sensor nodes, devices and so on. These sensor devices are connected themselves through different communication technologies. So, basically these different sensor devices are connected to one another, which in turn makes these different machines, the host machines, connected to one another. And these smart machines basically which have these different sensors produce lot of data which are typically analyzed either locally or off-site, maybe in a cloud or in a data center or something of that sort, and intelligent inferencing is made, and based on which maybe there is some actuation that is performed. So, here basically we are talking about smart machines, smart objects and so on. So, these smart machines are also smart because they can detect by themselves if there is any failure at any point of time, or in the production line if there is any failure in any point in the production line, and also if there is any machine downtime or production downtime or anything like that. So, everything will have to be detected on their own by these different smart systems, smart machines in these industries. So, we are talking about improvement of efficiency, productivity, health, safety, etc. of the systems. So, how can this be done? And autonomously, automatically basically these things are going to be detected, whether any machinery or any parts of the machines are defective or anything is going wrong or anything like that. So, everything has to be detected on their own. So, how it is possible? The core element for making it possible is the sensing element. So, we need to understand these sensors in more detail. So, before we do, let us take a recap also of the different applications of these smart sensing elements. So, smart sensors basically drive different IIoT applications, applications in the power sector, utility sector. So, smart power or utility, smart logistics and supply, smart communication, smart factory, smart manufacturing, smart car, smart robotics, smart city, smart grid, everything basically the smart component is primarily due to the existence of these smart sensors embedded in these different machinery devices and the system as a whole. So, we need to understand this part in more detail. So, if we look at the IIoT, right. So, IIoT, if we look at holistically, so at the very bottom is basically this smart sensing element. The smart sensors are at the very bottom of the smart sensors are basically at the very bottom. So, we have these different smart sensors and actuators in the bottommost layer. So, these smart sensors basically what they do, they sense and the sensed data are basically sent to some data center or some cloud or something like that for further analysis. So, before these are sent, the data basically the sensed data will pass through some kind of a edge or gateway device. So, these are the gateway devices through which these data are going to pass through, and then it is going to go through the core backbone network, maybe the IP network or something like that, and then finally the data will reach the data center where all the different analytics and storage are performed. So, this is this sensing and actuation, which is basically the most important part behind driving IIoT and the smart manufacturing, smart factory applications. So, what are the benefits of sensor usage in the industry? With smart sensors, we would be able to do real time autonomous monitoring of different machine parts, different processes, manufacturing processes, everything can be done in real time, monitoring can be done in real time. Then second utility is basically improving the visibility of what? Visibility of the machine status, the device status and so on. So, improving visibility. Operational efficiency will also be improved with the help of use of different sensors. Likewise, increasing productivity, improving quality efficiency, quality management efficiency, and then improving safety, minimizing downtime, improving the prediction and prevention of system failure, remote diagnostics. All of these things can be done in a much more efficient manner with the help of use of these different sensors or smart sensors. So, let us try to look at this sensing holistically in a smart manufacturing plant. Let us say that we have a manufacturing plant and we want to look at how these sensors play a role. So, we will start one by one with all these different elements. So, let us say that in this figure, as you can see, this is the central processing, controlling and storage unit. So, let us say that this is the central processing, controlling and storage unit, which is basically the central controller. Then where also the processing, not only the processing, but also the storage take place. Then we have the remote control unit. This is sort of like the control station from which the production processes over here are all going to be monitored. So, this is the remote control unit. So, basically this is the place from where the controller or the user is going to start the process with the switching on or off of any button, for instance, right. So, this is the remote control unit. Then we have this one is the production unit. We have the quality testing unit. So, basically after production, the different manufactured parts, let us say that these are the manufactured parts or manufactured products. So, these manufactured products basically will go through a conveyor kind of belt, and these different units are going to go through. So, the quality testing is going to be done over here, let us assume. Then the parts will get quality tested and move forward, and finally it is going to come over here, and we are going to have the counting of these different units of product taking place over here. So, counting will take place here, and then after counting the packaging takes place here, and as we can see over here we have a robotic arm or robotic device which is helping in this packaging, and finally the units that are manufactured are going to be boxed up, packaged and transported. So, the smart logistics etc. are going to come into picture from this point on. So, what did we see? We saw that these are the different components of a smart manufacturing plant, and these different components, as you can see, these are all these have different sensing units in them, and not only sensing units, but these units they can also talk to each other. So, they can sense and they can send the information to somewhere, right, and typically in this case this information is sensed and sent. All these different information from all these different units are going to be sensed and sent to this central processing unit or central controller or the storage unit over here. So, either it is going to be sent directly or through multi-hop communication, maybe through this particular node which is an intermediate node which is going to collect all this data from all these different points in the manufacturing plant and send it over to the central processor. So, we have this remote switch on or off, which basically starts the process or switches off the process, and that is from that central controller where the user is sitting, and then let us say that it is switched on, right. So, you turn on the process. So, once it is switched on, that data is sent to the central processing unit, and it is also sent to one signal is sent, unit signal is sent to that factory, the production plant, it is sent, right. So, the production process starts from here. So, then that all these data that are sensed and sent are stored in this central processing unit like this. So, the production starts, manufacturing starts, and then each of these manufactured units are going to be produced and put on the conveyor for further processing. So, the next step on is basically to quality test the quality of these manufactured products unit by unit. So, this unit is going to do this quality testing, and then this data is going to be sent from here in this particular scenario. As you can see, from this point it is going to be sensed and sent over here, and this is sort of like an intermediate hop, kind of like an edge device which is going to collect all these different data, and then either it will process partially over here or fully this data is going to be sent to the central processor. Then the product moves on, comes to this particular point where the counting of the number of units of production and the units which have been not only produced but tested over here, this counting takes place, counting of these products take place, and then this data again is sensed and is sent over here to that intermediate node. This intermediate node again sends it to the central processor for further processing and storage this information. Then the product moves on further, it is packaged, and that information again is sent directly, not over here, as you can see over here, this is showing that it is sent directly to the central processor. In the previous example, all these units were sending it to that intermediate node, and this intermediate node in turn was sending it to the central processor. And over here, this packaging unit, whatever information it has, it sends it directly to the central processor. And as I was telling you that there are two ways of doing this thing. So, one way is basically that you send it to some intermediate node and which is not far off from the point of sensing, and that basically is this example shown over here. And once it is done, the advantage is that you can have quicker response to the sensed data in terms of processing, but because not typically these intermediate nodes are not well equipped to do lot of processing, they are not very high power computational devices typically. So, partially they can do some processing, but then the rest of the information they will be sending it to the central processor like the data center or cloud or whatever for further processing. And in this case, in this example, the alternative was to send it directly to the central processor, and this is what this packaging unit is doing, sending it directly to the central processor instead of taking help of this intermediate node, and that is also an alternative, right. So, there are advantages and disadvantages of doing both. So, the product moves on further after these are packaged, and automatically the products are loaded on the trucks or any vehicle that is going to carry these products. The packages are loaded on the truck, and that information is also sent to that central processor. So, overall this is how these arrows basically show you where the sensing and then the communication took place. The sensing took place at all of these different points, but then these green arrows will show you how those sensed data are going to flow through this to this manufacturing plant to the central processor. This is what is shown over here. So, going back, we have seen that these sensing devices are very important. So, these sensing devices have the sensor which is actually the element which is sensitive to these changes of environment or any other thing that they are supposed to sense. So, these sensors are the central ones. Then we have the other components, the processor, the power management unit like battery or whatever. Processor is the one who will do little bit of processing, and then for communication typically it is the wireless communication module, but it is not necessary that it has to be wireless, but typically it is wireless in IoT, but it can be wired as well, or it can be a mix of both wired and wireless communication. So, this is the typical structure or the block diagram of an IoT sensing device. So, let us look at each of these sensors one by one. So, we will start with the temperature sensor. So, there are many different types of sensors that are used in the industries, and temperature sensors are the common ones. Temperature sensors are required to see or to monitor whether certain parts of the product that is being manufactured, the temperature of it stays below a certain threshold, or a certain compartment, a chamber in the factory is staying below a certain temperature threshold. So, temperature monitoring is very common. It is very much required in most of the smart factories and manufacturing plants. So, we have the example of a temperature sensor which is the analog variant, the analog temperature sensor. So, we can have analog temperature sensors, we can have digital temperature sensors. This variant, this model LM35 is an analog temperature sensor that generates analog voltage. So, this temperature sensor could be used in industrial applications to check the temperature or to monitor, continuously monitor the temperature of the different devices that are being used in the manufacturing process. In this example, this LM35 produces some output voltage, which is linearly proportional to the Celsius temperature. Okay, which is proportional to the Celsius temperature. So, we have in this case this LM35 comes with 3 different pins. One is this voltage one, the VCC, ADC is for analog to digital conversion, and then we have the ground. So, let us look at each of these components over here. So, this is an example of a temperature sensor, not the LM35, we do not have the LM35 model, but this is the one we are using, this temperature sensor, as you can see. And so, I told you that it has 3 different pins, right. So, one is basically the ground, the second one is for actually sending the signal, and the third one is for sending the highest voltage. Typically it is the 5 volts, it can be 5 volts or 3.3 volts. In this case, for this particular sensor it is 5 volts. So, this one, this blue colored wire is basically the one which is connecting to the 5 volt, right. So, this is this microcontroller to which this sensor is getting connected. So, this blue colored one is connecting to the VCC, this is the VCC, right, this is the VCC 5 volts. Then we have this ground, this ground is the black color wire, right. So, the black color wire is put on the is connected to the ground of this microcontroller, right. And then we have this white colored one, which basically sends the signal, the temperature value, the actual temperature value is sensed and is sent through this particular wire, right. So, this is how it is going to look like if you connect these sensors to the microcontrollers, right. This is how it is going to look like. So, we will go back and we will proceed further. As I was telling you that temperature sensors are very important. I have shown you an analog temperature sensor, but we could also have digital temperature sensors. The functioning of a digital temperature sensor is bit different from the way the analog sensors work. So, this is an example of a digital temperature sensor. The model is DS1621, and this particular sensor will generate 9 bits of temperature data, 9 bits of temperature data, this one. And this sensor, digital sensor, operates in the range 2.7 to 5.5 volts, right. So, the user can define the thermostatic settings using this particular sensor, and as you can see over here, it is connected to this processor or the microcontroller. This is this microcontroller unit, and we have the ground, the VCC, and these are basically the ports on the I2C bus. This SCL is basically for clock synchronization, and this DA is the one that will carry the data acquisition, for data acquisition. So, this is for the I2C bus, these ports are there, and these registers are the one which do the pull on. So, we have these pull on registers which basically help in this connectivity process in a certain way. So, I am not getting into the details of these pull on registers, but these pull on registers are required and they operate in the range 4.7 to 10 kilo ohms. So, we have then this output produced from the digital sensors in this manner, right. So, these are the different outputs which can be, so I told you that the outputs are basically generated as 9 bits of temperature data, and these are the last 3 bits that are shown over here, and we can have a combination of all of these, like it could be 000 or a permutation, basically permutation 011, over here it is 011, and these are basically the different sensors. I mean, each of these 000 will correspond to one type of sensor connection to one of these sensor device, then 011 for another one, and so on. Then we will have a look at another very commonly used industrial sensor, which is the accelerometer sensor, and this is this accelerometer sensor that is shown over here. This is basically how this ADXL 335 accelerometer sensor looks like, and these are the different pin configurations. These accelerometer sensors are connected to a microcontroller in this manner. The first one corresponds to this VCC, the maximum voltage of operation. Then you have these ADCs, ADCI, so 0, ADC 0, 1, 2 and the ground, and these are the ones which will be responsible for actually carrying the data. And why we have 3 ADCs over here? Because accelerometer data come as x, y and z coordinate values, and these analog voltages will have to be captured in this processor in this manner through these different ports 0, 1 and 2. So, let me show you the example of an accelerometer sensor over here. This is an accelerometer sensor. This is an accelerometer sensor. It is little small, so you will not be able to see it very well, but I think this will give you a fair enough idea if I tell you about how this pin configuration works. So, over here, as I was telling you that we need, so we have four wires over here, unlike the previous analog temperature one. So, we have 4 wires. So, we have 4 wires and we have 2 resistors. These are those pull on resistors that I was telling you earlier. These are the 2 pull on resistors, right. You can see these blue colored ones, these resistors. So, what are these pins corresponding to? What do they correspond to? So, the blue colored one, sorry, so these two, the blue and the yellow and the gray colored ones, they are the ones which basically connect the ground and the VCC, ground and the VCC. The red and the orange colored ones are the ones which are getting the accelerometer values, right. So, you cannot see over here very well because it is very small in size, but so what I would like to impress upon you is you can get any of these different sensors, look at their pin configuration. You can, if it is a open hardware, you can get easily get access to these pin configurations, and from these pin configurations you will come to know which pin basically connects to which port, right, which port of the microcontroller. So, this is then what you do is basically you connect the sensor to the microcontroller in this manner. This is the accelerometer sensor. Then we have another sensor which is also very common for industrial use, which is the gas sensor, and there are different variants of gas sensor. This MQ2 is a very commonly used gas sensor for industrial applications. It is an analog gas sensor. Here we have 3 pins only. One is the maximum voltage, the VCC, then we have the ground. Ground is basically like 0 volts. This is like your plus 5 or plus 3.5 volts, and then you have this ADC, right. ADC is the one which is actually carrying the signal about what has been sensed in that gas sensor. So, this gas sensor basically measures and detects the concentration of the different gases, and this has been made in such a way to monitor the concentration of LPG, propane and hydrogen in the form of analog voltage, right. So, like before, let me show you the example of a gas sensor. Let me show you the gas sensor. This is the gas sensor. This is a gas sensor, right. And this gas sensor basically, like the previous sensors, as you can see, has 3 pins, 3 ports. So, this you need to know, as I told you, that which pin basically corresponds to what. So, the red one basically corresponds to this VCC. This red wire is connecting to the VCC, which is the port for plus 5 volts. Then you have, there is another pin over here in this particular sensor, the way it has been made. There is a digital output which we are not connecting because it's we are interested in the analog variant of it, which is the analog output, and this analog output is connected through this blue colored wire, the green colored wire from this sensor to this microcontroller, and this is the one through which actually the signal about the gas concentration is coming. And then we have the ground. This ground is basically the one which is connected using the black wire. So, this is how you connect the different sensors, you connect to the microcontrollers. So, I have shown you 3 examples. The first one was the analog temperature sensor, then I have shown you the example of the accelerometer sensor and how it connects to the microcontroller, and this one is basically a gas sensor and how it connects to the microcontroller. So, temperature sensors are used in industrial applications such as petrochemical, defense, aerospace, consumer electronics, automotive and so on, and these are very important. Pharmaceutical industries also use a lot of these temperature sensors for monitoring the heat of the temperature of the liquids. Apart from temperature sensor, there could be magnetostrictive sensors which basically measure and detect the time varying stresses or strains in ferromagnetic materials. These are typically used for inspection of steel pipes, condition monitoring of machinery and detection of vehicle safety. Other industrial sensors are like torque sensor, pressure sensor, vacuum sensor, acceleration sensor, speed sensor, PIR sensor. PIR sensor basically detect the infrared radiation coming from the human body in its surrounding area. It is used for automatic doorbell closure, human detection, then the elevators in the lobbies, then common staircase and shopping malls. PIR sensors are very commonly used. IR actually stands for infrared, right. So, these are basically based on infrared radiation. Then we could also have other types of sensors like image sensors, ultrasonic sensors, like based on sending ultrasound, sound waves are sent. These are ultrasonic sensors are also commonly used for object detection, measuring distance, dynamic body detection, liquid level monitoring of tanks, trash monitoring, manufacturing process, automobile, people detection, etc. Other sensors are also possible, different other sensors for industrial applications like optical sensor, radiation sensor, level sensor, flow sensor, touch sensor, gas sensor and so on. So, in this particular lecture we have seen the use of these different types of sensors for making smart applications in industrial scenarios. We have looked at the pin configurations of 3 types of sensors: analog temperature sensor, then accelerometer sensor, and third is the gas sensor. And each of these different sensors, their pin configuration and how they connect to the microcontrollers, open hardware microcontrollers, that also we have seen. And this is the small building block which will be required to be extended further in larger scale to build smart factories, smart applications in smart factories and so on. Here are some of these references that you could go through. There are many others on smart sensing, and this is a topic by itself. Sensors are a topic by itself. So, you could basically find lot of literature on these different sensors, the way the sensors are made and so on. There are people who basically work solely on sensor fabrication, and for one type of sensor fabrication it may take several months to several years for fabricating a single sensor for the first time. If you are trying to come up with a sensor for the first time, depending on the type of sensor being made, the complexity of it and so on, it could take several months to several years to come up with the design of a particular sensor. And these are some of these common sensors that I have shown you, which are readily available in the market. So, you do not need to really worry about the designing of a particular sensor, the manufacturing of it, the fabrication of it, because that is a completely different ball game, and we really, unless we are very much interested and we dig deep into each of these, we will not be able to master the sensor fabrication so easily. It is a completely different story altogether. right now I am going to show you a practical demonstration of the use of PLC and SCADA based system. So, this specific system is about water distribution monitoring, and so we have a system in the School of Water Resources in IIT Kharagpur, and this particular system basically has end to end monitoring of water distribution, and it would be also extended for water quality monitoring. So, we have with us Professor Manoj Kumar Tiwari from the School of Water Resources, and also Miss Dina, who is the PhD student over here. So, I would request them to explain more about this particular facility that they have, and then we will also look at the applications of SCADA in water distribution. So, Professor Tiwari, what is this facility that you have? Could you please explain?
Yeah, thank you, Professor Mishra. So, actually this is a prototype of a water distribution network, the kind of networks that we see in the real field. So, there are you can see there are different pipe sizes. So, some are simulating kind of mains, then sub mains and branch pipe. So, the idea of developing this network is to test the things that actually occur in real field. So, this network or this system is equipped with various pressure sensors, flow monitors and actuators in order to control, monitor and operate it in the real time through SCADA and PLC based systems. Dina is working on this system, so she will further explain the details of the system.
So, Dina, could you please explain like how things work over here?
Thank you, sir. As already it has been explained that this is a prototype of a real water distribution network, and we all know that water distribution networks expand over vast areas, hence its manual monitoring is a pretty challenging task. So, the aim of our work is to devise a methodology of remote monitoring of these systems through the use of SCADA and PLC. When we come to a water distribution network, both quality and quantitative parameters are important, and right now we are monitoring only the quantitative parameters, which are essentially the pressure at intermediate locations of the system and the flow rate at the demand nodes of the system. So, here for example, we have a pressure sensor installed at the junction of the pipe network to give us the pressure at this point. Likewise, we have the pressure sensors at many locations of this network. Again, we here have actuators which are installed at different locations of the network. So, these actuators are actually control devices where we can control the rate of demand from the locations itself. So, here we have the actuators which are located at different locations of the network, and these actuators are basically control devices where we can increase or decrease the demand flowing through these locations in the network.
So, if I may add, actually it's there are the amount of opening, how much flow is to be maintained from this outflow junction can be controlled with such actuators. So, these actuators that way will be able to control the flow in a distribution network or a distribution pipe from a junction that way, and these actuators can be controlled remotely, can be monitored remotely. So, with the in the real time system, we always need not to go to the field in order to control the flow in a pipe or in order to sort of maintain the distribution or the demand from one particular sector.
So, the next component that I am going to show are the flow meters. Flow meters in a pipe network is essentially the demand node from where consumers can take the water for their necessity. So, here we have a manual paddle wheel flow meter which is connected to an electromagnetic flow meter for knowing the flow through the paddle wheel flow meter here. So, the electromagnetic flow meter is monitored remotely through the SCADA system, and the data will be available to us in our system.
Okay. So, Dina, what is this flow meter all about? What does it do?
So, basically the flow meter is installed here so that we know how much demand is consumed at the consumer point, and this data is required to actually in real systems, this data is required to bill the customers on the amount of water that the customer is using.
Okay, so everything can be monitored in real time
Yes,
through that
sir.
SCADA based system.
Yeah, so actually this flow meter essentially records the quantity of water flowing at a given instance, and then it has a totalizer also.
Okay.
So over a period of time, how much total water has passed through this pipe will be known to us.
Excellent.
And that is what actually is used while billing the consumers.
Okay.
Because how much water has been passed to their homes and what consumption they have made. So based on that, the billing for water can be done.
So Dina, could you explain a little bit further about this particular instrument, this flow
Yes,
meter?
sir. Yes, sir. So this paddle wheel flow meter needs to be pulled, and so this is how we open the paddle wheel flow meter. As soon as this paddle wheel flow meter is opened and the water flow is stabilized, the reading for the flow rate of the through this paddle wheel flow meter will be displayed here, and also the total amount of water passing through this flow meter over a period of time will also be displayed here.
So like right now, although there is no flow, so it is showing 0 meter cube per hour the instantaneous flow, but the totalizer is saying that it has been basically had over 1300 meter cube flow has been passed through in a given span of time. So from whatsoever this like the operation was installed or reset at 0 point. So from
Okay.
that point forwards, 1345 meter cube of flow has already been passed through
Okay,
this.
okay, wonderful. Is there anything else that you have over here? Other instruments that you might have?
Other instruments as such, like
Pumps.
there is weather monitoring station
Mhm.
that can be seen here. Okay, this also basically collects the data and transports in the real time the weather data. And from this network, the other interesting work which we are doing is because one of the major challenges in the real field network is in terms of water losses. So in India, the urban distribution networks only faces losses of the order of say 40%.
Okay.
That's a huge amount.
Right.
And there is no mechanism over there to basically detect these losses in real time, or and then because until unless we detect, there is no rectification possible. So first challenge is the detection. So with this, the kind of actuators we have, we artificially create leaks in these networks, and then developing a system for the real time detection of the leakages from the distribution network.
So Professor Tiwari, earlier you said that at present what you have is the water monitoring, particularly with respect to distribution, control over the distribution over the network, and can it be extended for monitoring the water quality as well at different points of the network?
Absolutely, definitely. So like whether we are monitoring a quality parameter or a quantity parameter, all we need a sensor. So like we have pressure sensors which are monitoring pressure in the distribution line. We can of course install water quality sensor like residual chlorine, pH, ORP, TDS. So there are sensors available for this, and if we install those sensors in this network, which eventually we might do, we have some idea of that. So when we install these sensors in these things, so we will be able to getting the real-time water quality parameters as well. So we can basically make the consumers assure that the water quality they are getting through their distribution network or through their water supply systems are of the potable quality or domestically usable quality.
So this the different sensor values, these are also tagged with the specific location from where this particular value is coming. So whether it is with respect to the quantity or quality, so the specific reading that is coming, so one can know that this is from this particular point or location from where this sensor value has come.
Absolutely, Professor Mishra. So all these devices, sensors can be geotagged also. Okay, so let's go downstairs, and there we can see that how these sensors located at different places are tagged in this thing.
So that you can know
similarly-
specifically
yeah,
that
we
from
know
which
specific-
location
absolutely.
the data
so
has
from
come.
which location, how much reading, or like we can monitor the specific locations in real time with the help of quality or quantity sensors.
Okay, thank you. So what we have seen so far is basically the water distribution network, the physical part of it, how the test bed showing the different water pipes, their branches and so on, how they have been structured, how they have been organized, how they have been located. So we have seen that. We have also seen that there are different sensors, IoT devices like water pressure sensor and different other water monitoring sensors are located at different points. And these values, the sensor values, also come tagged with the specific geolocation from where that particular value has come. So all of these things can be monitored from a central point where basically one can sit and monitor, have a look at the complete picture of the water distribution system. So we are going to go downstairs at the other location from where this particular facility has been installed, and we can have a look at how things are being monitored from that particular location. It is enabled with SCADA, it is enabled with PLC. So we are going to see how the SCADA and PLC based system will help us to monitor centrally the overall water distribution network. So we are at the control room, the monitoring point from where the water distribution system that you have seen so far can be monitored and centrally controlled. So on my back is basically the PLC controller, and on my left is the SCADA based system that can help in the supervisory control and monitoring. So what we have, I'll just show you what is inside this particular panel. So this is the PLC control panel. So as you can see over here, there is a lot of electronics and so on. So this is the main thing, the PLC controller. This is the main PLC controller. And Dina, can I now request you to explain the different other functionalities that we have over here?
Sure, sir. As you can see here, sir, the system of wires here are connected to the sensors on the top floor where we had already seen the system. So all the pressure signals and the flow signals are in analog form, and it is transferred to the system of wires to this location. So all these components here are basically to change the analog signals to digital form, and these components are for that purpose.
Right.
However, this is the main part of this system where these are the analog input signals, these are the two analog outputs,
Right.
and these are the digital outputs. And as you have already mentioned, this is the digital, this is the PLC.
So I will add a little more onto this. So because we have the network installed right over the rooftop of this own building, so we are getting the signals which are monitored from the sensors through these wires. But what happens in the real field, these SCADA systems or real field systems, when we apply it to the, let's say, larger distribution network, and there are the system is actually there in place at few places, so it becomes very difficult to get the wired signal from far off points.
Right.
So what we can use is we can use wireless technology. So the sensors that record the data, and through wireless communication it could be directly sent to the PLC.
Excellent. So basically what you are saying is that instead of using the wired technology, we could use wireless communication technology in order to send the data from the real sensors to this particular controller.
Absolutely, and it is actually in place at few, like it is already installed at few places.
And as you were saying that it is more useful and more convenient basically, because wireless technology you do not have to really dig the wires and through the
Absolutely.
you do not have to connect to the different cables.
Yes.
Okay.
So that becomes much more handy, because you need not to basically control the need not to install such a long wired system to bring all the information to the PLC.
Okay.
You can just, the sensor records it, and through wireless communication it directly sends to the PLC system. Okay.
Okay.
And the rest of the process then becomes
Right.
easier.
Okay, thank you. So on my right is basically the SCADA HMI, which basically helps you to graphically have a look at the entire water distribution system, and basically to have complete knowledge of from which point how much water is flowing through, and also if there is any leakage at any of the points, that also can be detected through this particular interface. So can you show us how we can monitor leakage in this particular panel?
Sure, sir. Sir, for an experimental purpose, if I want to create a leakage at a location, I will be using the actuators where I have control from the HMI. So here, as you can see, it is 0% now. That means
Right.
it has no leakage at all. So I just click here and I click the desired percentage of leakage that I want to create, and the same percentage of opening will be done in the actual system, and the water will flow through as it is shown here.
Okay.
So this leakage is actually monitored, like the detection of leakage what we were discussing is because this is an experimental network. So here we artificially create leakage,
Right.
and then through a software simulation we are which we are developing, we will be able to identify the location and to some extent the quantitative volume of the leakage.
Correct. Okay. So, Professor Tiwari, you have a wonderful facility over here. So the SCADA-based systems are available everywhere, and so this is an example of the use of SCADA-based system for water distribution monitoring and so on. And so this has been developed by one of the private firms. Can you speak a little bit about
it's
this
actually
firm
a
that developed?
Chennai-based company, MEL Systems Private Limited.
Okay.
So they have done this installation, and this is, as far as I know of, this is the first such facility in the nation,
Okay.
where we can, on a lab scale, we can basically monitor, control, and try to operate a water distribution network.
Right. And so basically with the help of this kind of installation, you are able to emulate the behavior of water distribution in a real kind of environment.
Absolutely, absolutely.
Thank you. With this we come to an end of it, for part 1, and then in part 2 basically we will go through in more detail. We will take up one of these different sensors, the gas sensor, and how you produce the gas sensors, right. So what is done. So I will show you how the working principle of a gas sensor is. Thank you.